Hi, I'm Prof and welcome to Chemistry Matters. And today we are going to talk more about equilibrium and specifically what happens to an equilibrium when you make a change to it. So, in order to discuss this, we're going to have a look at one particular equilibrium, and that equilibrium is carbon monoxide plus chlorine gas giving COCl2, which is called phosgene. And all three of those components will kill you quite happily, so a rather nasty concoction this. Okay, so what we're going to assume is that we have got a mixture of carbon monoxide, chlorine and phosgene, and that mixture is at equilibrium. So if it's at equilibrium, that means we've got some carbon monoxide, we've got some chlorine, we've got some phosgene in the equilibrium mixture. And we're going to take this equilibrium mixture and then we're going to make some changes to it. And we're going to be able to predict what way, if any, the position of the equilibrium is going to shift when we make each of those changes. Okay, so in order to do this, we're going to introduce a new concept. And this is going to be the reaction quotient. And we're going to call that Q, capital Q. Now, yes, it's a new concept, but the beauty of it is that it looks exactly the same as the expression for the equilibrium constant, which is a good thing, okay? So if we were going to write the equilibrium constant for this expression, we would say, right, Kc, it's going to be products divided by reactants. They're all in the gas phase, so we put them all in. So it's going to be the concentration of phosgene over concentration of carbon monoxide, concentration of chlorine. Now remember, we would normally put little e's there, E meaning equilibrium. Now, if we were going to write our QC expression, our reaction quotient expression, then the only difference would be we would take off those little e's. Simple as that. Okay? So, the expression for Q and K look identical. The only difference between them is that K refers to equilibrium values, which means that at any temperature, K has only got a single value. Now, Q, on the other hand, can have essentially an infinite number of values because Q is a non-equilibrium situation. Okay, so these can have any values that they want. So in other words, the actual value of Q can range between 0 and infinity, depending on the relative sizes of the top and bottom line of your quotient. Okay, the important point is that at equilibrium, and equilibrium EQBM, save writing out the whole thing, Q is equal to K. Okay, that's really important. So when the value of the reaction quotient is equal to the value of the equilibrium constant, we are at equilibrium, and the whole equilibrium position thing, we're not going to change it. Okay. Now, what we're going to look at now are situations where Q is not equal to K. We're going to take our equilibrium mixture and we're going to perturb it somehow, and we're going to make Q not equal to K, and we're going to see what the consequences of that are. Right, so the first thing that we're going to do, and I wish I hadn't rubbed that out because I'm going to use it straight away, is what happens if we add some chlorine to our equilibrium mixture. Okay, so we've got this equilibrium going on, it's all happy, nothing's changing, relative amounts of all of these three things are the same, and then we're going to pump some chlorine into the equilibrium mixture, and the question then is how, if at all, is that going to affect this equilibrium? So in order to answer that question, we're going to write our expression for QC, and again it equals concentration of phosgene over concentration of carbon monoxide, concentration of Cl2. Right, so we're starting at equilibrium. We're starting at equilibrium, so QC is equal to KC. because we're starting at equilibrium. Now, hopefully you can see where we're going to go with this. So we're now going to make a change. We're going to add some chlorine to this equilibrium mixture. Now, if we do that, we ask ourselves, what is the instantaneous effect on the value of QC when we make that change? Does it affect it? That's the first question. Second question, how does it affect it? If it does it make it larger or does it make it smaller? So, what have we got? We've got the concentration of chlorine on the bottom line of QC. Okay? So what's that going to do to the value of QC if we make this bigger instantaneously? Instantaneously. What does that do? Well, we're going to start off with Q and K being equal. We're going to increase the bottom line of a fraction, and if you increase the bottom line of the fraction, what does that do? It makes that fraction smaller. So the instantaneous change is going to be that we make Q smaller. So now Q has changed. Remember, K can't change because it's the equilibrium constant. It doesn't change. Increasing the amount of chlorine has increased the bottom line of the fraction. It's made Q smaller. That's the instantaneous change, and we're not at equilibrium anymore because Q doesn't equal K anymore. So what have we got to do to the system to make Q back equal to K? The answer is obviously we need to increase the value of Q. How do we increase the value of Q? We do that two ways. We can make the top line bigger, we can make the bottom line smaller. Both of those will result in Q increasing back to the point where it's equal to K and we're at equilibrium again. So in other words, making chlorine bigger is going to make Q smaller. We need to make Q bigger, therefore, to get back to equilibrium, and therefore that corresponds to a situation where we are going to go in the forward direction. We are going to make more phosgene. We are going to use up carbon monoxide and chlorine. Okay? So the first situation, what happens if we add chlorine to this? We're going to make more carbonyl chloride, more phosgene. Okay. You could use exactly the same reasoning to say, right, if we added phosgene to the mix, we would push things back that way. If we added carbon monoxide to the mix, we would push things forward. And we can do that all in terms of discussing what happens to the value of Q instantaneously after we make that change. Okay? So that's that sorted. Second question, what happens if we increase the pressure in the container by decreasing the volume? Okay? So let's write this now. We're going to decrease volume. What happens? Right. So again, we write our expression for Q, because if this change affects Q, then we're not going to be at equilibrium anymore, and we must get an equilibrium shift. So we write it out again. COCl2 concentration over CO concentration, Cl2 concentration. And you say to yourself, oh, well, this is easy. The volume doesn't affect Q because these values here are all concentrations. And you think to yourself, aha, no change. But you'd be wrong, because what does concentration equal? Concentration equals number of moles divided by volume, doesn't it? So therefore, in fact, we might find that QC does actually have a dependence on volume. How do we show that? Well, we now make the substitution. We write these concentrations in terms of N over V. So therefore, QC is going to equal the number of moles of phosgene over V, all over the number of moles of carbon monoxide over V, multiplied by number of moles of Cl2 over V. And you're thinking to yourself, ooh, that looks nasty. A fraction divided by a fraction multiplied by a fraction. Looks like nasty maths. But it's not too bad, because hopefully they taught you at school that if you've got a fraction on a fraction, You take the bottom line and put it all the way up the top, and you take this line and put it on the bottom of that one. And so this then is going to equal, we take this all the way up the top, it's going to equal V squared multiplied by the number of moles of CoCl2 over V multiplied by the number of moles of CO multiplied by the number of moles of Cl2. Okay? Now, we could care less about the number of moles of these things. What we're interested in is the volume. And so this then is going to simplify down to V squared upon V is equal to V times number of moles of CO, Cl2 over number of moles of CO, number of moles of Cl2. So here's the important point. Your value of Q depends on the volume. It's directly proportional to the volume. If the volume increases, then Q is going to increase. If the volume decreases, then Q is going to decrease. Okay? So what are we doing? We are increasing the pressure by decreasing the volume. And so therefore, let's use the same reasoning as we did before. We're decreasing the volume, so we're going to decrease Q. So therefore, we need to make Q bigger to get it back equal to K, to get back to equilibrium. So when we increase the pressure by decreasing the volume, Q drops. We need to make it bigger again. How do we make it bigger again? Exactly the same way as we made it bigger in the previous example. We make more of this, we use up these guys here. Okay? So if we decrease the volume, increase the pressure by decreasing the volume, then we are going to go to this side of the equilibrium. We're going to move the equilibrium towards products. Okay, that's that one. Looks like some pretty nasty algebra there, but hopefully go through and work that out for yourselves, and hopefully you'll find that it's not as nasty as it looks. Third example, what happens if we now increase the pressure by adding an inert gas, helium? Okay, we found in the previous example that when we increase the pressure by decreasing the volume, then the equilibrium goes towards products. Now, we can increase the pressure by adding an inert gas, helium. So what happens there? If we add an inert gas, nothing happens. Okay? Why does nothing happen when we increase the pressure one way, but something happens when we increase the pressure the other way? Because when we add helium, it cannot affect the value of Q, because helium is not in your Q expression. And that just seems totally wrong, doesn't it? Okay? That you can change the pressure one way and it has an effect. You can change the pressure another way, a different way, and it has no effect. Weird, but that's the way that it works. Okay? So adding an inert gas can never have any effect on the position of an equilibrium. And the final one, what happens if we change the temperature? Okay? What happens if we heat the reaction mixture? And the one thing that we need to know in order to answer this question is that delta RH for the forward reaction is equal to minus 109.5 kilojoules per mole. Okay? And knowing that, in particular knowing the sign of this, tells us which way the reaction is going to move, because we have this thing called the van der Waals equation. Okay, so d log K by dt is equal to delta RH standard upon RT squared. And you think, ooh, that's calculus, I can't do calculus. Yes, you can, because this is just a graph of log K versus temperature. That's all that means. A graph of log K versus temperature. And this says that the slope of that graph is given by the sine of delta H standard. So the sine of delta H standard tells you whether the slope of this graph is positive or negative. In this case, the slope of the graph is going to be negative because the sine of delta H standard is negative. So therefore it's going to look like that. Okay? So what does that mean? Well, it means as we increase the temperature, the value of k, or the value of log k, and hence the value of k decreases. Okay? So what does that then mean? Well, we write our k expression, Kc is phosgene concentration over carbon monoxide times Cl2. That's going to decrease. How do we decrease K? Fewer products, more reactants. Okay? That's going to decrease K. If we heat up this equilibrium mixture, it is going to go in that direction. It's going to go back towards reactants. So if we want to make lots of phosgene, the thing not to do is to heat this reaction up, because it won't work. It's going to push the equilibrium the wrong direction. Okay. Right, some good stuff there. Good solid equilibrium. Qualitative, in fact, aren't they? They are qualitative examples. We didn't really use a single number apart from this one here, and again, all that we needed to know was the sign of that. So this is the qualitative prediction of what's going to happen to equilibria when we start changing some of the conditions of an equilibrium. Okay, I hope you learned a thing or three about equilibria today. We'll see you in the next video.